For most of the history of astronomy, stellar death was governed by a single, irreversible rule. A massive star burns its fuel until the core reaches a breaking point. It collapses, detonating in a catastrophic supernova, obliterating the star forever. In 2009, telescopes captured what looked like a routine execution of this rule. An explosion flared up in galaxy NGC 7259 and was promptly catalogued as Supernova 2009 IP. But as the light from that explosion faded over the following weeks, astronomers found something that should not have been there. The progenitor star was still sitting at the center of the blast, completely intact. Then, in 2010, the same star did it again. It produced a second massive explosion, violating the standard logic that a star only gets one chance to go supernova. These events occupy a strange taxonomic gap. Astronomers call them supernova impostors, transient eruptions that release nearly as much energy as a supernova, but fail to destroy the star. If the core of the star didn't actually die, it leaves a hole in our understanding of stellar physics. There is no obvious mechanism that can generate an explosion of this scale while leaving the star standing. To find a precedent for 2009 IP, researchers had to look back to the mid-19th century. In our own galaxy, the Great Eruption of Eta Carinae serves as the prototype for these anomalies. In the 1840s, Eta Carinae became the second brightest star in the sky. It survived that eruption despite ejecting upwards of 20 solar masses of its own material into the surrounding space. We now know that these eruptions create an optical disguise. The ejected mass cools into a thick shell of dust that rapidly expands outward. This shell acts like a shroud, visually swallowing the star and making it appear as if it vanished from the cosmos. The unmasking happens in the light. This is the spectrum of 2009 IP, and those narrow peaks are the signature of hydrogen. These lines indicate the gas is moving relatively slowly, far too slow for the violent shockwave of a true core collapse. Supernova impostors are effectively a cosmic magic trick. The stars aren't gone. They are simply hiding behind the debris of their own near-death experiences. These tricks are the specialty of luminous blue variables, or LBVs. These are among the most massive and volatile stars in the universe. Inside an LBV, stability depends on the Eddington limit, the balance between gravity pulling mass inward and core radiation pushing it out. When an LBV flares, radiation pressure physically overwhelms gravity, stripping away the star's outer layers into space. This isn't a failed death, but a violent survival mechanism. The star uses these super-Eddington winds as a release valve, shedding mass to temporarily restabilize its core. But that stability is rarely permanent. In 2012, SN 2009 IP underwent a third eruption that was far more violent than the previous two. This time, the light curve didn't fade, and the expansion velocities jumped to 13,000 kilometers per second. That is more than 10 times the speed of a typical impostor eruption. Those speeds are the definitive signature of core collapse. After years of faking its destruction, the star finally reached its end in a genuine supernova. The timeline of 2009 IP forced a change in how we map the end of a star's life. We now recognize that these impostor events are often just a prelude, a violent phase that occurs in the final years before the terminal explosion. The most massive stars in the universe don't die quietly. These impostor eruptions are the warning sirens, an explosive,